Hello students, Dr. Regmi here. In today's lecture video, we will learn what is meant by half-life of a radioisotope, different applications of radioisotopes, and two main nuclear reactions type. Okay, we will explore about them. So let's start by understanding what do we mean by half-life. Okay, let's recall, we know that element do have different isotopes, right? Among these isotopes, some of them could be stable, some of them could be unstable. The unstable isotope, we call them radioactive isotopes. Okay, and these are the radioactive isotopes which undergo the nuclear activity. Right? We call it nuclear decay. So now, each of the different radioactive isotope will decay differently. Okay, so it means we will have a general feature called half-life. The half-life of radioactive isotope will be a property of that given isotope. Okay, so each isotope will have their one half-life. Okay, that half-life is independent of the amount of the sample, how much originally was there. It is independent of temperature and pressure and other factors. Okay, it is independent of those. So let's find out, what do we mean by half-life? Okay, we learned that half-life is a property of a radioactive isotope. Then what does it mean? So the half-life of a radioactive isotope is the time it takes for one half of the sample to decay. Okay, so what does it mean? It means half-life is the duration of time it takes from an original sample to reduce into the half amount of it. Okay, let's say we have 16 gram of phosphorus 32 originally. Okay, and then it starts to decay. Okay, radioactivity it starts, and in 14 days now 8 gram of phosphorus 32 has been converted into sulfur 32. Now we have just 8 gram of phosphorus 32 left. Means it has elapsed one half-life. The phosphorus 32 has 14 days, that is the half-life of it, because 16 gram has been reduced to now just 8 gram. Right? So the duration of time it takes for one half of the sample to decay is called the half-life. Similarly, if another half-life elapses, the 8 gram will start to decay and now we have just 4 gram left. After 14 days, only 2 grams of phosphorus 32 left. Right? So in this example, it has been one half-life, 2 half-life, 3 half-lives have been elapsed. Okay? In 3 half-lives, the original sample that was 16 gram is now just 2 gram. Okay, and we will find this half-life has a very useful for us, right? Depending on the half-lives of a radioisotope, we find applications in different areas. For example, here carbon-14 has a half-life of 5,730 years. Right? We use carbon-14 in archaeological dating. We call it carbon radiodating, right? Radiodating or carbon dating, in order to know the life of in order to know how much is the age of a certain artifact, we use the carbon-14 as a reference, right? Similarly, in medicinal area, we use a different therapy, like cobalt-60 is used for cancer therapy. We use iodine-131 for thyroid, right? Phosphorus-32 has a half-life of 14 days. We use it for leukemia treatment. Titanium, sorry, not titanium. Technetium-99 we use for vital organ imaging. It has a half-life of 6 hours. So it depends on how long is the half-life, and then we find the application. Okay, generally in medicinal purposes, all these radiation therapy, we would like to have such things like days and hours for them to work on, right? The geological dating or archaeological dating, they will be like something that has a very long half-life. We use them there, right? So nuclear, the uranium, which has a half-life of this many years, 10 to the power 8, right? So we use them in the nuclear reactors, right? We use uranium to get out the nuclear energy so that we can have electricity here. Okay, now how to use the half-life to determine the amount of radioisotope present. So let's look at our numerical problem here. Okay, we have a word problem to solve. If the half-life of iodine-131 is 8 days, how much of the 100 milligram sample remains after 32 days? Okay, so we are given the half-life, we are given the original sample mass, and we need to find out after the completion of 32 days, how much will be left over, right? So that is the question. So in order to know how much is left, we need to know how many half-lives have been elapsed here. Okay, we use the half-life as a conversion factor. So we need to find out how many half-lives occur in the given amount of time. 32 days, we have one half-life of iodine-131 is 8 days. So one half-life, right, is equivalent to 8 days here, right? So we use this equality as a conversion factor. So I have here 8 days is equal to one half-life. So days cancel. Now I have 4 half-lives here, right? So altogether I have 4 half-life and I have 100 milligram as a starting mass, right? Sample mass. So for each half-life, we need to multiply the initial mass by 1/2, because half-life tells us that half of the sample will be decay and half will left over, right? So for first half-life, I multiply by half, second half-life, third half-life, fourth half-life, because we just calculated 4 half-lives in earlier slide. So 100 milligram times half times half times half times half give you 6.25, because we have 100 times 1 by 2, 2 to 4, 4 to 8, 8 to 16, right? So we have 6.25 milligram of final mass. That is how we calculate. Okay. Now, let's see the application. We find the application of carbon-14 in archaeological dating. Let's have a little bit information about it. The radiocarbon dating uses the half-life of carbon-14 to determine the age of carbon-containing materials, right? Because the ratio of radioactive carbon-14 to the stable carbon-12 is a constant value in a living organism. Okay, so carbon-14 to carbon-12, this ratio is constant in the living organism. But once the organism dies, now what happened? The ratio on the value on this ratio get disturbed, right? Because the carbon-14 starts to decay. Now the ratio is off, right? The carbon-14 decays without being replenished, right? So now by comparing the ratio of carbon-14 to 12 in a particular artifact to the same ratio present in the organism today, the age of the artifact can be determined. So they just compare the ratio of carbon-14 to 12 in the current organism versus the old artifact, okay, similar one. So that's how they figure out, and we just know the carbon's 14's half-life is 5730, right? 5,730 years. So that is how they use it for carbon dating. Let's talk about a little bit about whether detecting or measuring radioactivity. The radioactivity cannot be detected by the senses, yet it can have a powerful effect, right? We will not know whether we are exposed to the radioactive materials at that point unless we see afterward. Aftermath, right? The radiation will damage or kill rapidly dividing cells such as bone marrow, skin, and reproductive and intestinal substances. That's why we use that radiation in therapy. So cancer cells divide rapidly as well, making the radiation an effective treatment for cancer. All right, so that's the application. The food is irradiated whenever we expose the food to gamma radiation. That will kill any living organism, the microorganism in the food, right? So for sanitation purposes, for hygienic purposes, we irradiate food or materials with some gamma radiation. Afterward, the food is not radioactive, it is germ-free, and it has a considerably longer shelf life. Okay, so that's the application. About the measuring, generally we use different units to measure the amount of radiation absorbed by the organism, right? Absorbed by the human or any substance. We go with the units like rad or rem. Rad means radiation absorbed dose. It is the amount of radiation absorbed by 1 gram of a substance. Okay, rem is the radiation equivalent for man. It is the amount of radiation that also factors in its energy and potential to damage tissue. Okay, so just few different units, and we use different units than these. Okay, becquerel or some other Curie units or something. 1 rem of any type of radiation produces the same amount of tissue damage. So we measure on the amount of tissue damage, and we express that in the rem unit. And during any kind of a treatment, we use different kind of isotopes. It depends on the half-life of that isotopes to choose which one. Generally, the technetium-99, the metastable one, we use them for the vital organ, bone scan, vital organ imaging, right? Like here, all these different things. We use iridium-192 for killing the cancers of the breast. We use iodine-131 for the thyroid tumors, right? So some examples are shown here. Okay, so now the 2 broad categories of nuclear reactions. Okay, so in earlier lecture video, we talk about all like alpha decay, beta emission, or gamma emission. All those nuclear reactions we talk about, those are of one category. In those cases, what happened is from a big nucleus, right, or from a particular nucleus, the other similar nucleus would form, and we would have some radiation, emission of some radiation side by side, right? So those were one kind of nuclear reaction. In this category of nuclear reaction, the one big nucleus will split into 2 smaller, similar size nucleus, and then we will have extra emissions. Okay, so I'm just showing the differences on the nuclear reaction we learned in earlier lecture video and the one that we are learning today. Okay, so we do have nuclear fission and nuclear fusion, 2 broad categories of nuclear reaction. Let's learn them one by one. Okay, nuclear fission, the word fission means it's splitting, right? Splitting apart of a heavy nucleus into lighter nuclei, right? 2 nuclei, and maybe some neutrons, some other emissions right there. It can begin when a neutron bombards a larger and heavier nucleus like uranium-235. Okay, so the same nuclear reactions, if we have like from one single nucleus, it gives out 2 similar size nuclei, maybe one is smaller than other, then we call it nuclear fission. In the meantime, there's some other emissions of small subatomic particles can happen. Let's see this example. We have a very heavy nucleus. We have uranium-235. Okay, and to induce such reaction, we need to bombard the uranium with a neutron. When this neutron comes and bombard, it hits, right, with the uranium. Now the uranium will split into, the nucleus of the uranium will split into krypton and barium. Okay, so we have here two nuclei, krypton with 91 mass number and barium with 142 mass number. In the meantime, we also get emissions of 3 neutrons. Now you can see these neutrons are capable of going back and hitting some new uranium, and that reaction can go on, and then we end up making chain reactions, right? Actually, this kind of chain reaction takes place if it is taken place very uncontrollable, right? When we do not have any control, the chain reaction go on and on. That actually happened during the atomic bomb, right? When the atomic bomb falls down, then this kind of reaction takes place and bringing a very big disaster, right? When these chain reactions are done in a very controlled way, so we do a very controlled way in the nuclear plants, right? And when we do that in a controlled way, we can harvest that very high amount of energy that comes out of this reaction. Okay, the energy is not shown in the reaction, but very tremendous amount of energy comes out as a result of this reaction. And the reaction takes place in chain over and over. You can imagine how big is that energy, right? And that nuclear energy, we call it nuclear energy, can be harnessed to get the electricity in the countries like our US. Okay, so the chain reaction we talk over here can be done controlled way or not controlled way, right? Controlled way, you get the electricity, brighten the city. If you have uncontrolled way, you bring the disaster to the city, right? So anyway, so that was the extra information. What we are learning here is nuclear fission, a nucleus of a large radioisotope can split into smaller nuclei, right? And also it can emit out some radiations or particle during that process. Another kind of nuclear reaction is nuclear fusion, right? It should have a fusion here, nuclear fusion. So nuclear fusion, now the name says fusion means it's joining together, it's adding up, right? So nuclear fusion is the joining together of two light nuclei to form a larger nucleus. When two small nuclei fuse together become a large nucleus, we call it nuclear fusion. Okay, example here, two different isotopes of hydrogen. We have deuterium and tritium. Okay, hydrogen with mass number 2 is deuterium. Hydrogen with mass number 3 is tritium. When deuterium and tritium bombard with each other, they undergo fusion. Now they fuse together to become the nucleus of a helium. In the meantime, the subatomic particle neutron is also emitted out. Okay, the fusion, the nuclear fusion is a very important nuclear reaction that takes place something on the surface of sun and other stars. Currently, we cannot use that kind of reaction because it requires extremely high temperature and pressure. So we cannot do the nuclear fusion in regular laboratory. Okay, so only that kind of temperature we observe on the surface of sun. So in the surface of sun, every time the fuel is the hydrogen, they are fusing and becoming helium, and tremendous amount of energy is coming out of the sun surface. Okay, so a very large amount of energy can be produced in the case of nuclear fusion as well as nuclear fission. And we learn both kind of these nuclear reactions in today's lecture video. Okay, so with this information, we conclude our chapter 10. Thank you.